In this video, we'll consider the properties of coordination complexes. Our learning goals will include the shapes of complex ions, those that include various coordination numbers, and the origin of color, which is really something that is a spectacular property of many coordination compounds. Let's first talk about complex ion geometry. Most complex ions have a coordination number of 2, 4, or 6. There are some others, but these are the ones that are most common. We're going to use the same kinds of considerations that we used in the VSEPR model to determine their shape. So for example, if the coordination number is 2 and the diamond silver 1 ion is a good example of that, we're going to expect to have a linear complex ion. Okay, the two ammonias are going to be on either side of the silver as far apart from each other as they can be. If there are 4, we will experience some tetrahedral complexes like this tetrachlorocobalt 2 ion. Okay, these things are again analogous to what we would see for carbon compounds, for example, that would have 4 bonds around it, and these would form a tetrahedral complex. But what's interesting about these complex ions is that we also see an instance of square planar complexes that involve 4 ligands. So this cisplatin is an example of a square planar complex. Now, it's often useful to know which one will form tetrahedral and which ones will form square planar. So I'll mention that most of the square planar ones are found particularly for complexes of rhodium, palladium, and platinum. We're not going to worry too much about drawing that distinction here. I want you to be aware, though, that square planar is a possibility when we have 4 ligands. The most common type of complex ion, though, has a coordination number of 6, and VSEPR model predicts then that it will have an octahedral geometry. In this case, this is the form of an octahedron, which is one of the Platonic solids, and the position of the metal is in the very center there. All the vertices around the metal are where the ligands will attach themselves, and there's a total of 6 equivalent sites in the case of an octahedron. They're all the same distance from the metal. If we want to draw this on a flat piece of paper, we would use wedge bonds to indicate those ligands that go into the page and those that come out of the page. So here's an example of hexamine chromium 3 ion. I want to make a special note that you notice that we've spelled amine in this case as AMMINE. When ammonia serves as a ligand, the way we refer to it in chemical names is by AMMINE, amine, that way. So this is just a peculiarity of the usage in this particular case. Let's now consider why things have color. So light from the sun contains all the colors that our eyes can see, and many more as well, some of the colors that we can't see. So what gives objects their color? Well, I want to consider what happens when you shine white light that contains all those wavelengths through some sample. All right, so here is a white light source on the far left. It contains all these different wavelengths of light. They're being shined through a sample that I show in a cylinder type cell. That sample will then absorb some of those wavelengths. All right, and as it absorbs those wavelengths, it only is allowing certain wavelengths to get through. So for the particular example that I'm showing here, it apparently absorbs the blue and the purple at one end, and it absorbs some of the red at the other end, which means that the only kind of light that gets through is green. So this sample would appear to be green to our eyes because that's the only light that gets through. Okay, colors also can arise from simply the reflection of light off of a sample, but in that case, it's still absorbing the wavelengths of light that we cannot see. So whether it's absorption or a reflection sort of principle, we're still going to see the colors that are not absorbed by the material. So how do compounds absorb light? Well, the energy of light is inversely related to its wavelength. So shorter wavelengths mean higher energy light, long wavelengths mean lower energy light. And the different parts of the molecule can absorb different wavelengths. So those different parts can include atomic vibrations, they can include the rotation of the molecule, can include the electrons. It turns out visible light is absorbed by the electrons in the molecule. And this is true in these metal complex ions. And we've also talked about how it's true in certain conjugated polyenes, conjugated pi systems. All right, the molecular environment can affect which of these wavelengths are actually absorbed. So some of the specific things that contribute to that are the identity of the metal and its oxidation state. These would both play a role in determining what wavelengths are absorbed. The identity of the ligands is also a very important factor. The geometry of the complex ion also affects this. So what we'll do is consider all of these effects as we think about the colors of these different complex ions. Now, it's useful to introduce a concept known as the Spectrochemical Series, and it's related to how ligands affect the wavelengths absorbed. We can arrange these ligands basically according to how strong their effect is. And an example of this is we have weak field ligands and strong field ligands, and the order in which they appear looks something like this. All right, you'll notice that iodide is at the far left end, so it is the weakest of the weak field ligands, and carbon monoxide is at the strong field end, so it is the strongest of the strong field ligands. Now, the way these are distinguished is that the weak field ligands absorb longer wavelengths, that is, lower energy light, so that's the red-orange end of the visible spectrum. The strong field ligands absorb the shorter wavelengths, or the blue-violet end. So depending on what ligand is there, we'll see different wavelengths of a complex ion absorbed. Now you'll notice that in this spectrochemical series, the ligand field increases as we move up from the bottom toward the top of the periodic table, and then as we move from the right to the left. So iodide is the weakest field ligand, and then as we move up through the halogens, you'll see that we're getting stronger and stronger field ligands. When we get to oxygen, then we're moving to the left, and we move through oxygen, nitrogen, and then carbon. And the two strongest ligands are ones that attach via the carbon atom. So that helps give you some idea of where this spectrochemical series is coming from. Now, I want to make one important point, and that is, don't memorize the spectrochemical series. If you ever need it for a problem, I will give it to you. Or if I haven't given it to you, you may always look it up in this lesson. This is not something to memorize, but I want you to understand and get an intuitive grasp for the fact that the identity of the ligand really matters and affects the color. So let's see an example of this. Let's look at copper sulfate. So here is a picture of copper sulfate, and it's initially hydrated with water. That is to say, copper sulfate is really this compound. All right, you can see that it's got a copper and a sulfate, but then it has 5 waters that are arranged around it in an octahedral complex ion. So this compound is bright blue, and it's bright blue because of the field that the ligands around the copper exert on its d electrons on the metal. Now, we can change this by heating this up. When we heat up this form of copper sulfate, it loses those water ligands, and it just becomes copper sulfate, an ionic compound. And you can see that when that happens, it loses that bright blue color, and it now is kind of a dull white sort of color. This is a spectacular demonstration of how those ligands really impact the color that these compounds have. So it is the combined effect of the ligands and the field that they form around the metal ion that gives rise to these special colors.